this second lecture on the solution of wave equation. Today we shall apply the wave equation. We shall solve wave equation in one dimension and apply the same to analyze the vibrating string. We consider the transverse vibration as set up in a string of length L fixed rigidly at its end, which are assumed to be at x is equal to 0 and x is equal to L. We know from our earlier study in earlier classes that in the fundamental mode of oscillation, lambda by 2 is equal to L, and in the first harmonic is 1, for which lambda is equal to L, and so on and so forth. Here we shall solve this problem by solving the differential equation. The vibration the transverse vibration as set up in this string satisfies the equation, one-dimensional wave equation, one by v squared del 2 u xt del t2, where velocity of the string is given by root over T by rho. T is the tension in the string and rho is the mass per unit length of the string. To solve this equation, we use separation of variable technique and we write x of x and t of t. When we plug this into this, and for non-trivial solution we have the left hand side is a function of x only and right hand side is a function of t only. So both the sides are equal to some separation constant. We choose the separation constant as minus kx square, which ensures the periodicity of space and time part, where k is called the wave vector. So the x equation becomes, the special part becomes d2x dx2 plus k square x is equal to 0. Now to get the solution as in the form for the x equation, the solution may be in the form of traveling wave, which is e to the power plus ikx and e to the power minus kx ikx. But here we assume the solution in the form of stationary waves, but because the wave traveling towards the right gets reflected from the end x is equal to L, and so there is a superposition of two identical waves traveling in the opposite direction, so stationary waves are formed. Similarly, the wave traveling towards the left gets reflected from the x is equal to 0 end. So we write the solution as A sin kx plus B cos kx. Now the time part is, the time equation is d2t dt2 plus k v k square t is equal to 0, or t of t is equal to c sin omega t plus d cos omega t, where omega is equal to v into k, the angular frequency. Now we come to the boundary condition. The boundary condition is that u of 0 t is equal to 0 is equal to u at Lt, because the string is fixed rigidly at its end, so there is no vibration or no displacement at the two ends, which this boundary condition in terms of x becomes x is equal to 0 at x is equal to L. X is equal to 0 sets b is equal, this condition leads to the case that b is equal to 0, and this condition gives you KL is equal to n pi, that is to say k cannot have continuous value, k can have only few discrete value, and this is given by n pi by L. So there are only few selected values of k, and the corresponding solutions are obtained as this equation. We get knx is equal to an sine of knx is equal to an sine of n pi lx. Then this solution is also becomes independent, and this we get Tn is equal to Cn sine omega nt plus Dn cos omega nt. We call this constant C prime and D prime, so we call un of xt, where n can have values 1, 2, etc. So un is equal to xn of x times tn of t, so which can be written as an sine omega nt plus bn cos omega nt times sine knx. If we write this explicitly, this becomes an sine omega n. Omega is this, so that we have omega n is equal to v times kn. This is n pi v by l, n pi v by l. So this is n pi vt by l plus bn cos of n pi vt by l sine of n pi x by l. This is the solution for a particular value of n. Since the differential equation under consideration is a linear differential equation, so the most general solution is the superposition of all solutions. Un of xt. So this is an sine omega nt bn cos omega nt sine knx, and velocity v at xt is given by del u del t. From this relation we get n is, we get it by differentiating partially with respect to t. Sometimes when we set the string in motion, we get we are supplied with two initial conditions, that is the initial velocity. Initial condition is initial velocity u0 of x is equal to u at x t is equal to 0. If we set t is equal to 0, this term is not there. We have this term always this is, and initial velocity v0 at the function of x is v at x0. This is from this relation is summation over n is equal to 1 to infinity a n omega n sine of knx. If we know the u0 and v0, then bn and an can be obtained as we have done in Fourier series. You know that u0 of x is equal to summation over n is equal to 1 to infinity bn sine of n pi x by l. We multiply both the sides by sine m pi, so we write u0 of x sine of m pi x by l, integrate it from dx from 0 to l. On the right hand side we have bn, then within integration 0 to l sine of n pi xl into sine of m pi xl dx. This part, this integration is equal to summation over n bn l by 2 delta mn. So this is equal to L by 2 bm, or we have bm is equal to 2 by L integration from 0 to L u0 of x sine of m pi xl dx. Similarly, the knowledge of v0 gives you, similarly we get am is equal to 2 omega ml 0 to L v0 of x sine of m pi x l dx. So if we were provided with the values of a0 and u0 and v0, we can find out the expansion coefficient. For Planck string case, u0 of x is not equal to 0, but v0 of x is equal to 0. Since v0 of x is 0, am would be 0, but bm would be non-zero, and consequently there will be this term will not be there. And for Stokes string case, u0 of x is equal to 0 and v0 of x is a delta function x minus. So in that case we see that since u0 is 0, b is 0, but it is not 0. So we can get different cases from this initial conditions. Up till now, we have solved the one-dimensional wave equation by using separation of variable technique. there is another very convenient way of solving this differential equation and getting at the solution like this, from the which can be obtained from the Dalembert's method of solving differential equation of one-dimensional wave equation. So we are going to describe a Dalembert's method or Dalembert's solution of the wave equation. So we start with this differential equation. Dalembert's solution of 1D wave equation. The differential equation that we start with we introduce two variables xi, x plus vt, and eta is equal to x minus vt. So when we take the partial derivative with respect to t, this becomes del xi, del t, del xi, del eta, del t, del eta. So this is simply del xi del t is v del xi, and del eta is minus b del eta. So this is, if we take v common, this is del xi minus del eta. So that del 2 del t2 is equal to v square del xi minus del eta to the power 2, which is v square del 2 del xi 2 del 2 del eta 2 minus twice del 2 del xi del eta, and del x is in this way, del x is equal to del eta del x del eta plus del xi and del eta del x del eta. We see that this is 1, so this is del xi del xi plus del eta. So del 2 del x2 is simply del xi del eta raised to the power 2. This is del 2 del xi 2 del 2 del eta 2 plus twice del 2 del xi del eta. Now if we substitute this in the differential equation, so if we substitute for this del x part, we get del 2u del xi 2 plus del 2u del eta 2 plus twice del 2 del xi del eta is equal to, this term has to be multiplied by 1 by v, so del 2u del xi 2 plus del 2u del eta 2 minus twice del 2u del xi del eta. This term cancels with this cancels with this, or we have del 2u del xi del eta is equal to 0. If we integrating with respect to eta, we get del 2u del xi is equal to some constant some function which is independent of eta, so it is a function of xi. And if we integrate with respect to xi, now let me explain this step once again. We differentiate, we integrate it with respect to eta, so there will be an integration constant which is independent of eta. Here we assume it to be a function of xi. And if we integrate it, we get u as f of xi d xi plus a quantity which is independent of xi, so it can be chosen to be a function of eta, and we call it f of xi. This is the solution. Now if we write it explicitly, this becomes f of x plus vt plus g of x minus vt. The boundary condition is that u at x is equal to 0 at all time t is equal to 0. That is, from here it is f of vt plus g of minus vt. This shows that g of minus xi is equal to minus f of xi. That is to say that we can assume the solution to be u as f of xi minus f of minus xi. That is, the solution can be taken to be f of vt plus x minus f of vt minus x. For xi we write x plus vt, so minus of xi means this thing. Now we have another boundary condition. That is, now we have u of xt is equal to f of vt plus x minus f of vt minus x. U at lt is equal to 0. This gives up f of vt plus l minus f of vt minus l, or f of vt plus l is equal to f of vt minus l. So the f is periodic with spatial period is equal to 12. So if this is so, we can expand f of xt and f of minus xt in Fourier series. So we expand f of vt plus x as a0 by 2 plus summation over n is equal to 1 to infinity. This is an, and the argument is vt plus x for this, and time period 2n pi by 2l. So this is 2 cancels out, n pi by l is the argument. Vt plus x plus Bn sine of n pi L Vt plus x, and for this part we write f of Vt minus x is equal to a0 by 2 an cos of n pi L Vt minus x plus Bn sine of n pi L Vt minus x. So the solution u of x t is f of Vt plus x minus f of Vt minus x. So that is to say this minus this. So a0 term goes and we have n is equal to 1 to infinity a n. Then cos of this minus this, n pi L Vt plus x minus cos of n pi L Vt minus x plus Bn this is the Fourier solution. Now this is this part. This is twice an cos this minus this. This is equal to sine of n pi Vt by L times sine of n pi x by L, and from this part we get, with a minus sign, and this twice Bn cos of n pi Vt by L sine of n pi x L, which is this is the same solution as we have obtained by solving the partial differential equation. This is another reason for saying the solution that we obtained is the Fourier solution, because it can be obtained from the Fourier series as well. And this is also called the harmonic solution because it is the superposition of harmonic terms. So this is all about the wave equation in connection with vibrating strings. In the next class we shall take up the wave equation when applied to stretched membrane. We shall consider two cases. One is the membrane in the form of a rectangular as a rectangular membrane and a circular membrane, and we we solve both these two cases, and see what would be the eigenfrequencies.